Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will discuss a phenomenon known as evanescent waves, which is again something that we do not discuss usually when we talk of total internal reflection, and then carry out a matrix analysis or formulate a matrix method of analyzing reflection from multiple layers or multiple boundaries. Okay. So, we go back to the total internal reflection and evanescent waves first and then carry out the matrix analysis. Well, this is the Ki and Kt vectors, the incident and the transmitted wave vectors, which we are considering. We are of course considering only the total internal reflection phenomena, therefore, the first medium or the medium of incidence has a larger refractive index compared to the second medium, which has a lower refractive index. Okay. So, this we call as optically dense medium, this we call as optically rarer medium. So, denser and rarer medium. Now, we have seen these expressions Kt, the wave vector, is equal to the magnitude of the transmitted wave vector Kt cos theta t z hat plus Kt sin theta t x hat. This is obtained by simply decomposing the transmitted wave vector into two pieces, right. We know that the transmitted fields will have some transmission coefficient, whether that is Te or Tm transmission coefficient, but that times there is a phase factor e to the power minus j Kt dot r. This is what I am very interested in. Substituting for Kt, you see that this phase factor can be neatly decomposed into a phase factor which is z dependent and phase factor which is x dependent, right. Now, consider what happens when theta I is greater than theta Ic. We have already seen that in that case cos theta t becomes imaginary, correct. So, this becomes imaginary, which means we have to rewrite cos theta t as some j times let us call this as I do not know what we should call. So, let us call this as j alpha. Okay. Now, I have two choices here, should I consider as plus j alpha or I consider minus j alpha, right. But let us try and see what happens to the phase factor when we consider plus j alpha and minus j alpha and substitute that one into this expression. So, not alpha, let us put out a different term for this. So, instead of plus j alpha minus j alpha, let me call this as plus j alpha prime and minus j alpha prime. Okay. So, when I substitute that back into the term e power minus j Kt cos theta t into z, what happens to x is not really important because sin theta t is not getting imaginary. So, what happens to this one? Well, you have e power minus j, now Kt is as it is, cos theta t has become complex. So, I will put j alpha prime into z. What is the product of minus j into plus j? The product of minus j into plus j is plus 1. Therefore, this says e power Kt alpha prime z. Now, alpha prime is real, Kt is real, z is real and it is increasing as you go into the second medium, right, which means this wave keeps on increasing in its amplitude as you go deeper and deeper. Okay. Clearly, that cannot happen, there is no amplification happening, no amplifiers are connected. So, this choice of plus j alpha is wrong. Okay. If we choose minus j alpha, what will happen? Instead of a plus j here, I should replace this plus j alpha prime by minus j alpha prime, in which case you have minus j times minus j times minus j is minus 1. Therefore, there will be a e power minus Kt alpha prime into z. Okay. This will actually decay as you go deeper into the second medium. Now, that is more like okay, I mean you know that the waves can decay, but the waves cannot amplify and go off to infinity as z keeps on going to infinity. So, this minus Kt alpha prime, because Kt is real, alpha prime is real, can be rewritten or redefined as a single alpha. This alpha can be, I mean this Kt into alpha prime can be redefined as alpha itself. So, you have Kt alpha prime and therefore, what we see is that along z the waves are exponentially decaying, while along x they seems to be oscillating or traveling. So, it is a very interesting phenomenon in which the wave actually starts to transmit along the interface, but its strength reduces as it propagates and goes down in the into the second medium. So, it is there in the along the normal to the interface, if you keep going, the amplitude keeps on dropping off as e power minus alpha z, where alpha is equal to Kt times alpha prime. whereas along x it continues to oscillate. These waves which carry no energy but they can excite other modes or other structures are called as evanescent waves. Okay. The evanescent waves are very important because if I choose one more structure, so I have already chosen this one to be such that N1 is greater than N2 and this is N2. If I now choose a structure, let us say N3, and bring this structure closer, so let us say I choose the structure over here N3, not very far away. Okay. If I choose it very close by to this medium and let us say N3 is greater than, or sorry, N3 is less than N2, then the waves that are present here can actually excite the propagation of additional light that is formed by this structure of two parallel lines, or this is a film of some refractive index N3 that you can think of, and it can actually excite waves or wave propagation, or as we would actually call it, the mode propagation, or they excite the modes of this particular film which is formed by this purple color lines, okay, or between those two purple color lines. So this is the way of what is called as evanescent wave coupling into optical waveguides, which was very important in the 1970s and 80s when optical integrated circuits were first developed. Even today this is sometimes used, instead of having any generic boundary you actually put in a prism, okay, such that you constitute, so you send light into the prism but you have the prism slightly above the optical film. So if this is the optical waveguide, you have a prism over here, you choose the gap such that you actually, there are a few considerations in choosing the gap, but the gap has to be chosen such that it is not very far or not very close, but an optimum gap if you choose, and then have light incident into the prism, okay, and arrange the prism to the gap boundary to be a total internal reflecting boundary, then light will be reflected back into the prism, okay, but there will be evanescent waves generated from prism in the gap, and because of this film that is now kept, right, it would generate modes inside the film, okay, and you would actually couple light and excite light into the second medium. So this gap coupling by evanescent waves is a very common technique that was used and is sometimes used even now in coupling energy or coupling light into the second medium, okay. But we have not really found out what is the value of alpha. Well, in one sense we have, alpha is given by kT, right, kT can be kT times alpha prime, kT is nothing but the frequency omega square root of mu 0 epsilon r. Now which medium should we consider? This is the second medium that we need to consider, right. So this can be rewritten, so times epsilon 0, so this is nothing but k0, which is the free space wavelength or free space propagation vector as we would call it, which is given by omega square root mu naught epsilon naught times n2. N2 is the refractive index of the second medium. What is alpha prime? Alpha prime was this cos theta t, right, when theta is greater than theta ic. So this was actually square root of n1 square sin square theta I divided by n2 square minus 1, okay. So you can rewrite the value for alpha as k0 square root of n1 square sin square theta I minus, so this n2 square can be multiplied, and when you pull n2 out, that will cancel with the numerator n2. So this is the value of alpha that we were looking for, which corresponds to how much attenuation or how quickly the fields are falling off in the evanescent region. So this completes our analysis of evanescent waves and the total internal reflection. Now what I want to consider is a very interesting topic. If you want more details on this topic, I ask you to look at this book by Ghatak and Tyagarajan. It's a very interesting book called Optical Electronics. If you want even more details, you can look at book called Optics of Layered Media. I believe that this is the correct title, and this is by Yariv and Ye, okay. So you can look at this book, or you can look at this book for the simplified analysis. The idea, I mean the development what we are trying to do is to put in some kind of a matrix method to analyze multiple layers, okay. The goal is to analyze a scenario where you have different layers or different material media. This will have a refractive index n1, this will have a refractive index n2, and this will be at a certain length or thickness of d2, this has n3 and a thickness of d3, N4 thickness of D4 and you have N5. So, this is a scenario where you have 1, 2, 3 and 4 layers, okay, and 5 different media out there. Well, we have already seen one way of understanding the propagation here. So, if suppose I send light in the normal incidence here, I know that there will be a reflection back into the first surface, there will be a partial transmission into the second surface, right, second media, and because of the interference, because of the interface between second and third media, there will be partial reflection and there will be transmission, there will be reflection, there will be further transmission, further reflection, and eventually you will see that light, a partial amount of light has come out, okay. But for mathematical sense, we also put in a back reflected or the excited kind of a source, although there is nothing here. So, that is why I put this in the dotted lines, right. So, it is one way to analyze, one way to analyze this particular structure is to actually rewrite this one as a transmission line. So, you actually have a transmission line here, right, and then connected to a different transmission line. So, let us say connected to a different transmission line, then you connect it back onto another transmission line, then one more transmission line, which finally is the last medium is considered to be a load, okay. So, this is another transmission line and this is the load, okay. So, in between you have to write down what is the thickness or the length of each of the transmission lines, and you can actually analyze the problem in this way. There is you have to successively first find the impedance here, then transform to the impedance here, then transform to the impedance here in order to obtain the overall reflection, and in fact we have asked you to do that in one of the programming exercises given in the first week modules or something, okay. So, you can analyze this way, but this is, well, this is one way, but there is another more popular way, okay, of analyzing these multi-layer films as we would call them, and that involves the use of matrices, okay. Let us develop this matrix analysis just for a single film or two boundary scenario. Extension to multiple layers is extremely simple, we will talk about that one. The scenario that we want to analyze is given by this one. So, you have a second medium of thickness D2, okay, having a refractive index of N2, while in the third medium I have refractive index of N3. The first medium or the incident medium has a refractive index of N1. For simplicity, I consider only the normally incident waves, okay. So, you could of course extend this analysis to the oblique incidence case as well, but in the oblique incidence case you have to keep in mind whether are you analyzing TE modes or TM modes, okay, and you have to use the corresponding formulas for gamma TE and transmission of TE appropriately, or gamma TM or transmission coefficient for TM, and keep calculating theta t at every interface. Now, there is a little bit of complications out there. So, we want to avoid that complications to get you the essence of the method, and this is the simplest case that we can think of is that of a normal incidence, where there is no calculation of theta t will be equal to 0, theta I will also be equal to 0, okay. Before we can begin the matrix analysis, just as a reminder for ourselves, what are the electric fields in the incident region? There will be an incident field which would be propagating, let us say this is the z direction that I have chosen. So, this would be E1 plus e power minus j k1 z, k1 corresponds to the incident wave vector, okay, and there will be a reflection wave also because of the first medium interface between the first and the second medium, that will have an amplitude of E1 minus 1, meaning this is the first medium, minus indicates it is the reflected light. So, it would be travelling positively in this way. Inside here you have, let us say, E2 plus e power minus j k2z, and the reflected light would be E2 minus e power j k2z. This node is z equal to 0. Since this is z equal to d2, we write this as E3 plus, and instead of writing this as k2z, it would be better if we write this as k3 z minus d2, okay. Otherwise, you will have to keep track of this e power minus j k z or k d2 kind of a phase factor. I do not want to carry this phase factor, therefore, I choose my coordinate system itself such that z equal to d2 stands as the z equal to 0 kind of a plane for the third waves in the third medium. As I said, there is nothing coming off in this direction, I have not kept my source here, yet if suppose I had that one, at least mathematically I can write this as E3 minus e power minus j, sorry, e power plus j k3 Z minus d2. Okay. So, these are the waves that I have, and these waves are actually going along in this particular way. What about the magnetic fields? Well, the magnetic fields will have for the positive Z travelling waves, right, or the waves which are propagating along the forward direction, they would all have the amplitudes reduced by the appropriate medium refractive index, not medium refractive index, by the impedance. Since impedance is inversely proportional to refractive index, the amplitudes of the H fields will be multiplied by n. Okay. So, H is E by eta. Since eta is inversely proportional to refractive index, H will be n times E. Okay. And for forward waves it would be positive, and for the waves which are propagating along minus Z, that is reflected fields, they will be minus n times E minus, right, because these are propagating along minus Z direction. Okay. So, the H fields have to go along minus, so that if the electric fields are along x, then x cross minus y should give you along minus Z. So, this is the amplitude, but let's not put that one down right here. We will do that one once we write the boundary condition for the first and second medium. Well, boundary condition for the first medium. What is the boundary condition here? I know Z equal to 0, so E1 plus E1 minus must be equal to E2 plus E2 minus in terms of the electric field. What about the magnetic field? Well, this would be E1 plus N1 minus N1 E1 minus to be equal to E2 plus, which is N2 E2 plus minus N2 E2 minus. Okay. So, this for the electric fields, these are for the magnetic fields. Now, this gives you two sets of equations. I can rewrite these equations in terms of the matrix form by writing this as the left hand side as E1 plus and E1 minus. Okay. This can be written equal to as a matrix S1 times E2 plus and E2 minus, okay, where I will leave this matrix to find the matrix S1 as an exercise for you. You just have to add and subtract the equations after multiplying appropriately. So, you can take this N1 onto the right hand side, add the two, then you will express E1 plus in terms of E2 plus and E2 minus. Similarly, if you subtract, you will express E1 minus in terms of E2 plus and E2 minus. So, if you do that one, you will realize that this can be written as 1 by T1 1 R1 R1 1 E2 sorry. So, that is the S matrix. Okay. So, the S1 matrix, which is applicable at the first boundary Z equal to 0, seems to have a structure in which it is a 2 by 2 matrix. Okay. Because we are not considering the polarization, this is a 2 by 2 matrix, otherwise you will have to consider a 4 by 4 matrix. So, T1 is the transmission coefficient from the first medium to the second medium, and R1 is the reflection coefficient from the first interface. So, clearly R1 is equal to N1 minus N2 by N1 plus N2, and transmission will be equal to 2N1 by N1 plus N2. Okay. So, these are something that you already know of. So, let this exercise, you calculate that exercise, calculate that one, and show that that is the correct expression. Now, what is the boundary condition at Z equal to D2? Well, this is the second medium interface, right. So, again if I calculate that, there will be a phase factor for E2 plus. So, that would be E2 plus e to the power minus j k2 d2, correct, plus E2 minus e power j k2 d2. This should be equal to E3 plus E3 minus. Okay. Similarly, for the magnetic field, if you apply, now that would be N2, right. This is N2 E2 plus e power minus j k2 d2 minus N2 E2 minus, this is the reflected magnetic field, this must be equal to N3 into E3 plus minus E3 minus. Okay. So, I hope you do not have any difficulty in writing these equations. Now, you can substitute k2 delta d2 as a some number delta 2, okay, and rearrange the equations again in the matrix form with the goal that you express E2 plus and E2 minus, which are the fields in the second medium, in terms of the matrix S2 times the fields in the third medium, E3 plus and E3 minus. Okay. So, when you write in this way and calculate what is S2, you will see that this would be equal to 1 by T2 e to the power j delta 2 R2 e power j delta 2 R2 e power minus j delta 2 and e power minus j delta 2. Okay. So, please verify where delta 2 is of course K2 into D2. So, please verify that this matrix what we have written is the correct matrix expression that we have. Okay. Now, what is the advantage of writing all this? Well, I have expressed E2 plus and E2 minus in terms of E3 plus and E3 minus, but I already know that E2 plus and E2 minus, right, times S1 was equal to E1 plus and E1 minus, right. Now, this is nothing but S1, since E2 plus and E2 minus is related to E3 plus and E3 minus via the matrix S2. So, I can rewrite this as E3 plus E3 minus. So, essentially what I have is a single big S matrix, okay, which will be equal to S1, S2 all the way up to say S of n minus 1, provided you have n number of media that you need to consider. So, for each media you will have to find out what is the corresponding matrix S, okay, and that structure of the matrix S is very easily written down here. For S1 we have written, S2 we have written, for S3 you can very easily write this as 1 by T3 e power j delta 3 and so on and so forth. Okay. So, this overall S matrix will be a 2 cross 2 matrix, and therefore, you can even write this as A, B, C and D. Okay. Thus, relating, so you might have multiple layers, okay, so you might have multiple layers out there, but if the incident fields are E1 plus and E1 minus, and finally the transmitted fields are say En plus and En minus, although as I said this does not exist if you assume the source to be located in the first medium, and for whatever the distances or whatever the thickness of each of the materials be, and for whatever wavelength, you can easily change the value of k and obtain the new values of delta, and for this case you can write down the overall relationship between E1 plus and E1 minus as a big matrix S times En plus and En minus. Okay. So, this overall matrix, as I said, will be a 2 by 2 matrix, can be written as A, B, C and D. Now, obviously, I know that in this scenario I do not have any En minus. Okay. So, after writing all the entire matrix, I can substitute En minus equal to 0. When I do that, I see that E1 plus is simply given by A times En plus. Okay. This is the final transmitted electric field, this is the incident electric field, and then you have the reflected electric field E1 minus related to C times En minus, right, so Cn En plus. Okay. Now, if you want to obtain what is the ratio of say En plus by E1 plus, which should tell you the overall transmission coefficient. Okay, this is just the amplitude ratios, these are not the power ratios, these are amplitude ratios. This would be equal to what, 1 by A, because E1 plus is equal to A times En plus. Similarly, if you now want to find out what is E1 minus by E1 plus, which is the overall reflection coefficient, this would be equal to C by A, right. So, that is all that is there to this one. Now, let us specialize, or let us carry out the analysis for the case of the single film and 2 layer condition that we considered, okay, in the previous development. And for that case, that is for this particular case, you have the medium 1, medium 2 and medium 3 with an appropriate length of D2 or the phase factor delta 2. The transmission coefficient, sorry, the reflection coefficient R, which is related to the magnitude square or squared magnitude of the reflection coefficient. This is the overall reflection that we are talking about a single film, and this would be equal to R1 square plus R2 square. You can show this, I will leave this as an exercise for you. R1 R2 cos of 2 delta 2 divided by 1 plus R1 square R2 square plus 2 R1 R2 cos of 2 delta 2. Of course, you can find what is the transmission. So, this is the power transmission coefficient as 1 minus r, because these are powers are actually getting conserved, power or energy is getting conserved. Okay. Now, let us see this power reflection coefficient or the reflected power. As we start varying delta 2 either by varying the thickness of the film d2, there comes a point when cos 2 delta 2 will be equal to pi. This will happen whenever 2 delta 2 is some odd multiple of pi, correct. So, whenever there is some odd multiple of pi, when this happens, is that correct? Yeah, cos 2 delta 2 is correct. So, delta 2 can be written as 2m plus 1 into pi by 2, but that is okay. So, whenever the argument becomes pi or in one of the odd multiples of pi, cos 2 delta 2 becomes minus 1. So, the numerator for this can be rewritten as r1 minus r2 square, okay, and the denominator can be written as 1 minus r1 r2 whole square. So, this would be the value for power reflected, which is r1 minus r2 whole square by 1 minus r1 r2 whole square. Now, we are actually at a very interesting point. Suppose I consider a film and I take the same medium as the third refractive index medium, the third medium to be having the same refractive index as the first medium. So, clearly R2 and R1 will be, let us say this is the refractive index 1, the next one is about say 3 and next one is also 1. So, then what is R1? R1 is 1 minus 3 by 1 plus 3, which is minus something, so minus 2 or something, so minus 2 by 4 or something, right. Similarly, what will happen to R2? R2 is given by N2 minus N1, which will now be equal to minus R1, right. So, when that happens, then R2 will be equal to minus R1. So, I can substitute for this in the expression that we have derived, and I obtain reflection R to be some 2 R square divided by 1 plus R square. Okay, there is nothing much interesting happening out there. Okay. Suppose I adjust this in such a way that R2 equal to R1, then capital R can be made equal to 0, right. So, I can actually have no reflection coming back and the entire light could be transmitted into the second or transmitted into the medium out there. Okay. We will see what kind of a solution that needs to be employed in order to solve this problem, in order to make R equal to 0 in the next class, where we discuss two important applications. One is the multi-layer film, that is whatever we have discussed, we will extend the analysis from one layer to the multi-layer case, okay, and make a few of the remarks about that. And then we discuss one film scenario where this kind of a situation is employed in order to make it act like a resonator called as a Fabry-Perot cavity or Fabry-Perot cavity resonator. We will see these two applications, but before that you should do these exercises and actually verify, convince yourself that the expressions that we have obtained for the overall transmission coefficient, reflection coefficient, and for a single film the expression that we have obtained is actually correct. So, until then, thank you very much.